All right, we're here. We're out here. Let's get it. Let's get the chat pinned. Start it up. What a good start to an album. Can you hear that? All right, we got that pinned. We got our first question on screen. This is the new year. Okay. Hopefully, I'm singing voice isn't too terrible. All right. Code off. Stay a while. Actually, I'll be right back. Let me get the sweater. No. Oh, jacket sweater.
So everybody put your best suit or dress on. Let's make believe that we are wealthy for just this once. Lighting firecrackers off on the front lawn as 30 dialogues bleed into one. I wish the world was flat like the old days and I could travel just by falling. No more airplanes or speed trains or freeways. There'd be no distance that could hold us back.
Hey, Sarah, we're doing some physics to start here. Let's get it. Sketty. Sketty. Alright. Are we in? Do you read me? Do you caught me? It's the new year. All right. The new year. All right. All right. In good shape. Okay. Let's get the tablet out. We're almost there, folks. I know. It's pathetic. Maybe get the tablet clean just the tiniest bit. Get a little wipe down. A little wipe down of the tableau. Could make the mouse go crazy here for a second.
Hi,
Let's
it's
wipe
Brian,
down.
and I'm a Walmart pharmacist.
Tableau.
Flu shots are coming soon to your local Walmart
Oh,
pharmacy.
okay.
Be the first to know when appointments are available by setting up a flu shot alert at walmart.ca/health
Shot.
or ask your local Walmart pharmacist for more information.
Oh God. Tell me I got a broken thing here. Be right back, folks. Alright, I was going a little crazy here for a second. Alright, we're in good shape. We're in good shape. All right.
Your heart is a river that flows from your chest
All right.
through every organ. Your
Okay.
brain is the dance.
So we've got our question on screen. Let's tackle it. All right. Let me know if music is no good. So, two masses, M and M. Okay, I'm already just gonna change them to M1. No, let's call that M2 and that M1. So this is
Instincts are misleading.
1.
You shouldn't think what you're feeling.
That's M2.
They don't tell you what you know you
Okay, so M2 is bigger. Attach to each other a rope that runs around a mass hanging pulley. Mass M. Okay, so how do we know M2 is bigger? Because it says M2 here is going to go down. So if we imagine this sort of system, if you had a rope, you know, over a plank of wood, let's say, right? And you had a heavy mass on this side, and you were sort of holding on to this. That's supposed to be a hand, but let's not worry about it. Right? So you're holding on to the rope here. Well, if you let go, that thing is going to fall, right? Okay, but let's say that instead of letting go, you sort of have a peg here, and you wrap it around the peg, and you tie it around the peg. Well, then it will just hang there. It'll eventually reach some new equilibrium, right? So this is going to be our sort of like at rest at the start. And what we're sort of trying to get to here is this new spot where it's fallen some distance x. But before we do that, let's sort of like just talk about the physics here of what's naturally going to happen. You should know, you have an instinct here. So, okay, you're holding a weight over a plank, right? You've got a rope thrown over a plank of wood, and as you pull it down, the weight gets pulled up, right? And as you let go, the weight goes down. So instead, you tie it to a peg, right? Eventually, the peg will sort of like just be pulling as much as the weight needs to reach a new equilibrium. Okay, now let's say instead of a peg there, instead of tying that to a peg, you tie that to a spring. So there's a spring here, right? Well, what's going to happen is that spring is going to stretch to the point where it's fallen. And how are those two springs different? So this here should be kind of the distance x, what they're describing here. How much the thing has stretched, how much, because this is, you know, at equilibrium. They say the spring is at equilibrium, it's unstretched. So any movement here would be how much this thing is stretching, right? And so we're going to do a kind of, you know, energy situation, because we have elastic, we have kinetic, and we have gravitational potential. So, you know, let's not do all the force or kinematics of that stuff. Let's do the energy. So what we're going to do is we're going to say the energy at one circumstance is going to be equal to the energy sometime later. They may have transferred between certain forms, but it's going to be the same amount of energy from one to the other. So, okay, I'm going to turn this music down just a tiny bit. Oh god. Okay. So, okay, so the energy total at one time is equal to the energy total sometime later. Yep. So that amount of stretch there now has some elastic potential energy. And this is some spot 2, right? So let's actually draw. This is some analogy where we were in a barn lifting some weight attached to a string or something. This is now our same system. So I wonder if we could maybe even steal this. Let's do it. No, because like we can do this. Or I mean, this is a silly one to do. I don't want to do this. There we go. We at least don't have to draw a pulley. We got a perfect pulley, bro. My pulleys are perfect. Okay, there we go. So, some time later, once it's after falling X, and is this centimeters? Don't think we're given it, so we're just gonna say meters, X meters. Okay, so this thing has fallen X meters, so I didn't start a podcast. Why are you accusing me of this?
Stay in the loop, even when you're
What are you talking about?
Try YouTube.
Okay, I am in the loop. Kamash. Okay. All right.
Sometimes I think the cycle never ends. We slide from top to bottom, then we turn and climb again.
All right.
And it seems by the time that I have figured what it's
Nice. Let's just check in the stream health. Be good. Right?
my place in line and I have waited the
All right. So, after falling some X amount of meters, so this sort of distance is X, which means this thing has kind of climbed X. And that's now where M1 is. And our spring is stretched now also by X. Right? So, you know, this isn't perfect, but let's just say that's our kind of X value there. Let's maybe make this a little smaller. Ah! Okay, we don't want to do that. Waiting for the crazy. Okay, let's make that just a little bit bigger. There we go. Okay. So, okay, let's do it. So the energy at one circumstance. So we're going to talk about EE, we're going to talk about EK, we're going to talk about EG. What's the circumstance here? Well, let's make it easy on ourselves. Let's call that spot H equals 0. This is an unstretched elastic thing, so that's 0. It's not moving, so that's 0. And we chose a nice little height of 0 meters right where it is, so the whole thing is 0. So that means that the energy that was sort of transferred around have to still sum to be 0, okay? This is never a bad idea to make your initial energy equal to 0, because then your second energy becomes who are the energy givers, who are the energy takers, and they have to be equal to each other. okay? Instead of being equal to some like 200, right? Which would have maybe been the total for 1. Okay? Regardless of whether you understood that or not, we have to reach a total of 0 joules because E1 was 0, so E2 has to be 0. We can't create or destroy energy. Okay? So let's do it. So 0 is equal to E2 here. So we have the elastic potential energy. Okay, and I'm just going to call it EE because we didn't even have anything here, so we're not really going to get confused. We're not going to use that EE anymore. So let's just call that EE. And this I'll show you why in a second here, because we now have EK1, which is how fast M1 is moving. How do I know that it has kinetic energy? What is kinetic energy? It's the energy of movement. So my claim is that this thing is moving. Do I know whether it's moving? Does it matter? You could still have a kinetic energy when you're not moving, but it's 0. So do you have it or not? I mean, that's a question, but who cares? Not philosophy. So we also have the gravitational potential energy of M1. This thing has now risen by X. So going up is against gravity. That's gaining some energy, right? And then we have the kinetic energy of M2, right? Which is also to say, I don't know whether it's moving, but let's just put it in there and say it might be moving. And then we also have the kinetic energy of 2. Sorry, the gravitational potential energy of 2. Now, let's be careful here, because which one of these energies, these are all of our energies now, that are found at E2 that are relevant. Okay, we could also maybe burn these boxes and get some chemical potential energy, but we're never really going to use up or add to that value, so we won't really include it in the total, right? With energy, we're almost always interested in the change in energy, not really interested in the actual true total. Okay, so here we're just sort of saying the change is 0, so all these givers of energy better equal all these takers of energy. So who are the takers of energy? Who gained energy? Right? We can also use the language of work to describe this. So the spring did positive or negative work. Did the spring gain energy or lose energy? The spring gained energy. So the spring did negative work. Negative work is stealing energy. Right? Doing work is using up your energy. Doing negative work is stealing energy. Okay? So the spring did negative work equal to the elastic potential energy that it's now found. That's now found at 2, right? So, I almost just wrote with a pen on my tablet here. So that's now equal to positive 1/2 kx squared, the energy of a spring. Okay, the kinetic energy of M1, is this going up or down? Well, it started at 0, and you can't really have negative value, so it is going up. So again, another stealer. So this thing did negative work, right? And we won't really be able to say yet who they're stealing from, and because we haven't identified any givers of energy. So let's just keep going down the line. Maybe we'll see some givers. If we don't see some givers and they're all taking energy, then that's not okay, because they all can't take energy. Somebody has to be giving it up. They can't create energy out of nowhere. Okay? So 1/2 mv, sorry, that's m1 v squared, right? That's the speed it's now going. I don't really know what that speed is. And now mg delta h. That's also a positive value. Why is it positive? Well, because the gravitational potential energy went up, right? So M1 rose, and that takes energy. So that's kind of like a negative work as well, right? Okay, so what about the kinetic energy of 2? That's also positive for the same reasons as the first one. But do I have to specify 2 different velocities here? It's an important question. Because Because what? Are they moving at the same speed? That's my question. Yeah, the speed that I let go of the box, M1, is the speed that M2 is going to be lowered. Right? Imagine, remember, you're there, you know, like bring yourself there, right? Remember times that you've held onto ropes and resisted some, you know, force, right? Okay. I think my volume might be a little bit high. How is my volume here? I'm just going to turn myself down just the tiniest bit. Okay. There we go. So, okay. So that's a steal of energy as well. So that's some negative work, and it's the same velocity, right? Which is also good because we want, our goal here is to derive an expression for speed, right? So that's the speed we're talking about. Now, this is, for now I'm going to write plus, okay? But what happened to the gravitational potential energy of M2 from spot 1 to spot 2, from time 1 to time 2, from when it was at rest before we let it go to when we found it sometime later, not necessarily stopped, but just having moved some distance x? Well, it's gone down, which is, you know, for now I can just write mg delta h here, right? Let's now specify the two delta h's, delta h1 and delta h2. So what is delta h1? And maybe let's just get kind of all the values that... Oh! Wow! What are you doing, bro? Wow! What are you doing? There we go. Okay. Delta H1 is positive x, how much it went up by. Delta H2 is the negative x. That's important, right? Because, you know, this is the world where up is positive, right? So that x might be equal in magnitude, but negative and positive matters here, right? Because that was an energy that went down. Okay. So let's kind of like keep simplifying this equation. Let's maybe do this, just kind of move this down for a second here. And let's just keep simplifying this equation a bit. So 1/2 kx squared plus 1/2. Okay, I'm just going to multiply everything by 2 instead of having to write all the 1/2s. I'll just add in a 2 where I didn't have a 1/2. Okay, so kx squared plus m1 v squared plus, and I didn't have a half, so now I have a 2 mg. The delta h1 was positive x, so I'm just going to put x plus, now I had a 1/2 and I multiplied by 2. You know, 0 times 2 is still 0. So m2 v squared plus, and this one didn't have a half, so now it has a 2 mg, and the negative matters here. So let's change this plus to a minus, okay? And now our goal is to rearrange for v, right? We want a v equals this. That's what we've been asked for, right? So let's do this. Let's take these two and anything that has them in their term. So that means I'm going to kind of, for now, have to grab that whole thing because I can't separate those for now. But let me just kind of put all the other ones on the other side, right? So besides those, I'm going to keep those on this side. And all the others I'm going to move to the other side. Okay? So let's... For some reason I can't. There we go. Okay. Keep all those on this side, and the other ones I'm going to put on the other side. So I'm going to get a 2 mgx minus kx squared minus 2mgx. Ooh. Okay. Wait a second here. Look. Maybe we could simplify this before we Can we simplify that? No. Made a mistake here. What did I do? I didn't put the M1, the M2, so this is M1. This is M2. This is M1. This is M2. So this is M2. This is M1. Right? Okay. Never before. Okay. So we can't simplify those, but we could do some factoring, right? Okay. And left over on this side is our M1 plus M2 kind of factored out from a V squared, right? So to derive an expression here, we're going to get the square root of, and let's see if we can do some factoring. So let's do, the 2's don't really factor, but, or maybe we can just do this. 2G that. Is that right? I know it's not necessarily recommended, but yeah, I think we're good, right? And then so that over M1 plus M2, and then square rooted. There's an expression for the speed that has fallen some distance x. Not bad. Alright, Captain. Okay, so find, let's move these down a bit. Down a bit. Into the down a bit. Okay, here we go. Find the speed of m if... Okay, so wait, are you just giving me all the constants that are in here, right? I think so, yeah. So let's just find the speed, right? So remember, this is M2 and this is M1. And let's just kind of like make sure this makes sense. So this thing has traveled 46 centimeters, right? And so 46 centimeters is like half a meter, and so that's like, you know, 75 kind of Newton source of energy from that thing moving down. Okay, about, let's just say. So, okay, so then that makes sense, right? Like 75. Okay, so a little bit goes into this, and the other little bit goes into that, right? Okay. So square root 2g times m2 is 15.6 minus 3.5 minus kx is 95 times x, which is 0.46. Careful to not use centimeters. All over 15.6 plus 3.5, right? Okay. So, just testing our calculator skills, I guess. Let's do it. I'm up for the challenge, bruh. I'm up for the challenge. Did I screw this up? Maybe I'm not up for the challenge. Oh no! I did. Okay. That's okay. Okay, minus 99 times 0.46. Got it. Okay, then times 0.46. Got it. Then divided by, yes, 15.6 plus 3.5. Boom, sada boom, and then a square root u, and we get 2.16. How many sig figs? Looks like 2, so 2.2 meters per second, right? This is velocity, and we converted everything, so we're good. Beautiful.
Discover new songs with YouTube
Okay.
Music, a dedicated
so not
music
so
streaming
scary.
service. It's
Right,
designed
but
to help
not
you
bad.
quickly
This
find
is like
music you already
university
love,
mechanics,
discover new
right?
songs to fall in love with. Start a free 1-month trial of YouTube Music
Alright,
Premium.
let's take it from
Personal
there.
Guide to the world of music.
So we've got a small commercial break, and then boom. Okay. FK is constant. What does that mean? FK. Okay. Block of mass M is released from rest and slides down a rough incline with inclination angle theta and coefficient of friction, kinetic friction, mu k. At the lowest point in the incline, the block continues to slide along a circular track of radius r, as shown in the, okay, so comes down a slide, has friction, and then does it have friction on the track? On the loop? It experiences a kinetic friction force Fk of constant magnitude. Interesting, okay. So if the block has enough kinetic energy to slide past point C on the circular track, draw a few diagrams for the box at point C and D. Excuse me? Okay, sure. So let's maybe say C. Let's start at C. So we've got 2 free body diagrams that they're asking us for here. So boom. And boom. Okay, so this is, let's use that for D, and we'll use this for C. Okay. So I'm just going to kind of use a dot this time. Just, you know, sometimes I use boxes. Most of the time I use boxes, I'd say, but some people just use a dot there and don't really use a box to write in anything. So, you know, and this is a good opportunity because the mass is the same for the whole thing, right? The mass is just m, so I'm not even gonna write it. Okay, cool. Okay, so a block of mass m is released from rest. Okay, so it slides down from rest, sure. So we might have to actually do some kind of work to figure out any sort of, you know, actual values. But to just do the free body diagram, we just need to know that it's kind of like still on the track. So if it's on the track, first of all, is it on Earth? Yes. So in both, we have our... so we have our FG, right? In both cases, no matter what. Okay. Good. What else? So D, let's not worry about D for now. Let's just talk about C. It might be a little simpler. C is traveling in circular motion. Does that mean we have a centripetal force? A force that pushes us towards the center? No! No, we do not. We do not. Centripetal force, the force that causes circular motion, is, you know, to think of it that it's there as if it's a new force is a backwards idea. What we have to do is to do the Fnet. We have to figure out what forces are there, okay? And then the circular motion part is us saying, ah, it's moving in a circle. That means the Fnet is towards the center. So we know that this thing should ultimately have an Fnet downwards here, and D, it should have an Fnet in that direction, towards the center of the circle, right? So that's kind of an interesting idea, yeah? The F net is the centripetal force. It is not a new force. 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 Okay. So, we're told about some forces, right, in the problem. It says, while the block slides along the circular track, so this is both C and D, it experiences a kinetic friction force, Fk, of constant magnitude. So it's going to be the same in both, which is nice, because Fg and Fk now are going to both be the same, right? But what's going to change between C and D? It's the direction of that, right? So in D, the friction force is going to be sort of opposing what direction it's moving, and in D it's kind of moving along the track, so that means that friction is going to be kind of down and to the left, right? Opposing that circular motion right at that spot. It's going to be down and to the left. But what about at C? Well, at C, remember, the sort of like overall motion is on its way this way, and the surface kind of like does this. So backwards in that world, or sort of like opposing the direction of motion, is just perfectly horizontal, right? Okay. Now, there's got to be some, you know, there's got to be some force from the surface, right? How do we know there's some force from the surface? We know there's some force from the surface. Well, the equation for friction uses the force from the surface. So if there's friction, there has to be a force from the surface, the normal force, right? So we know there's a normal force. Remember, normal force is always opposite or sort of perpendicular to the contact surface. So it's like that for C, and for D, it's like this. Yeah? So C is straight down is another, let's not put that, let's move it then. It's blue. So straight down is Fn, right? And what about in D? It's kind of up and to the left, right? In fact, it's the same direction as that F net is supposed to be, right? Okay. So let's I mean, are we done? Are we done? Are there any other forces? I don't think there's any other forces at any of these two spots, right? So maybe something we could do is do a rotated system and get our sort of like X and Y components, but I don't know if it's going to be worth it. Okay? I think this should be okay for what they're asking. Okay? So okay, beautiful. There's our C. And there's our D. Alright, beautiful. So what is the minimum sped the box should have at point C so that it does not fall off the track? So it does not fall off the track. Okay, so that's sort of asking the question, you know, what speed would give a Fn of 0, right? Where the surface doesn't push back because you're not in contact anymore. What speed would give that? Okay, and then you have to be like a tiny bit more than that. So let's say, for example, you figured out that, you know, a speed of 20 meters per second would, you know, give you a normal force of 0. Because as you go faster around this, right, picture it, as you spin something like faster, as you throw something faster through there, it's going to have more force against the surface, right, as it kind of goes around it. Well, that means the surface is going to push back with just as much force. So it's going to push back more. So the less speed you have, the less the surface is going to push back. To the point where you don't have enough speed to get up, because this, and that's the surface like losing contact. So that's what we're talking about. So let's say we figured out that it was 20 meters per second that we needed to get to, right? Then we would, I mean, as an answer, we would just give velocity is greater than 20 meters per second, right? Because then anything greater than that should have a velocity of, or should have a normal force. Sorry, I'm sort of like thinking about, you know, the best way to approach this next time. So what is the best way to approach it? What is the minimum speed the box should have at point C so it does not fall off the track? So we're gonna basically be looking at a free body diagram that doesn't have Fn, but because it doesn't have Fn, are we allowed to not have Fn and still have FF? No. Right? The equation, remember, the equation for FF is mu times Fn, right? The harder you want friction to be, the harder you push down on an object, which causes the surface to push back harder. That's, you're increasing the normal force, you're increasing the friction force. You can also increase the grippiness, that's increasing the mu, right? The coefficient of friction. So that's the kind of two ways that we can increase friction. Well, if you don't have a surface pushing or a surface in contact with something, then you don't have a friction force, right? What are you creating friction with, right? So what does that mean? That means we have okay, sorry, this okay. Sorry. So let's do it. So let's kind of like do C without Fn and without FF, and let's say that Fg is my net force that is causing circular motion, so it's Fc, which is mv squared over r, right? And so actually it doesn't matter what mass it is. And so let's just see what we're told here. What's the minimum speed you just have at point C so it does not fall off the track?
Catch every move and dive deeper with music videos
Well,
and behind the scenes extras.
do we know the radius? Let me just see.
Sign up for
So we
YouTube
can
Premium
cancel
and get all
those,
your videos
right?
ad-free
So we
and
get
offline.
the
Try 1 month
speed
on us.
is the square root of r times g. And what is r? Are we told r? No, it's just, we're just told it's r. So there it is. Okay, so that's a minimum speed that will just get to C and then kind of like keep going, and then it'll stay on the surface ultimately, but you know, you have to go technically slightly more than that. So like, let's just say V is greater than that value. Okay. So actually, let's do this. Okay, so V has to be slightly bigger than that. Okay. From what height h above ground level should the lock be released? The lock? Block? Be released? Why are we missing a bunch of letters? Above ground level should the block be released in order to just make it to point C. Ah, okay. So what they're talking about here is, let's kind of like grab, I think what we can do is just grab this diagram. And actually let me do this for a second here. Take those off. Do I need that? Let's just get rid of that. We don't need that. Come on.
All the girls
in every girly magazine can make you feel any less alone. I'm reaching for the phone. Call 703 on your machine at home for you to come home. Boom. But I know it's too late. So the energy total at any one spot has to be the same. So let's kind of like do the inventory. So E at 1 has to be equal to the energy at 2. E at 1 is made up of gravitational potential energy, it's made up of kinetic energy, and it's made up of, that's it. There's nothing else, right? Or maybe friction, actually. Okay, so let's just say it's made up of that. It's not, there's no friction there yet. But E2. So E2 has gravitational potential energy, because that's still at some height. It also has some kinetic energy. Right? It is moving. We said it's going this velocity. Right? And there was also some work done to friction. Right? We kind of lost some energy to friction. So let's sort of say that, you know, that was found in those two and it got released and sort of, you know, it's not found in those two. So this is fair for that equation. Right? Okay, so I'm going to cheat a little bit. I'm going to make my lowest spot, even though it's not the ground, I'm going to make my lowest spot my 0 for height, right? So all I really have to do is sort of say, like, you know, what is this? This is like H, and this is 2R, right? So, E1, EG1 is the mass times G times H minus 2R is my height, right? This big height minus this little one will give me this value here. So this is H minus 2R, the kind of difference there, right? And now EK is 0. It's not moving, right? We let go of it, so it's not moving. And we don't give it any velocity is another key part there. EG2, this is something that we've chosen to be nice and easy, which is nice. That's why we did it. Missing that turned into an F, it should be an E. Do we know how fast that's going? Well, it is traveling, let's just say, right at that velocity, right? But it's not just purely that, it's 1/2 mv squared, and v is root rg, so that's really just rg, right? And then plus the work from friction, which we kind of don't know just yet, right? Okay, so from what height h above ground level should the block be released in order to just make it to point C? No, the box is about to fall off the track at point C. Okay, so okay, so to find the work due to friction, work, remember, is the sort of average force with the, you know, if we're going to do this in vectors, it might be the dot product. For us, let's just kind of do this as a scalar, that it is, well, I mean, obviously the result of a dot product is still a scalar, but the average force times the distance that the force was acting over, right? Okay. So we know the sort of force, right? In fact, we can kind of break this down here into a kind of like work done over the first section plus work done over the second section, right? So that's from like, well, okay, how about we do A to B, work from A to B, and then B to C, right? Because we go from A to B, and then B around the circle to C. So we're going to have this length, and then what should we use for this length here? What should we use for this length here? Well, should we use the circumference or should we use the 2r? We have to use the circumference because that is the distance, the friction sort of like, you know, if we were to lay this all out, it's extended over that whole distance, right? So, okay, so now mu k, which means to find the force of friction there, we need the force, the normal force, which means a free body diagram of that thing. So let's just kind of quickly do that. The normal force, this is going to be straight down Fg. That is going to be our kind of surface. That's our Fn, right? And do we have anything else? I don't think so, right? So this is our force of friction. It's kind of opposing the motion, right? And it does fall down, so we don't have any sort of obligation or knowledge about Fnet equaling 0, but we do know that vertically the Fnet equals 0. So that's going to be enough to kind of like get us our answer. So, okay, so that angle there is theta. If you're not sure of that, then like this here makes it a little easier. This is our rotated system, where we sort of rotated our head. And how much did we rotate our head by? We rotated it by theta. Another way to think of that is our original Fg was vertical, and now we've kind of slammed it over here to go from star to star is angle theta. Another thing to see is that it's kind of like down and to the right. Fg is here, so like you wouldn't accidentally put it over here because that should look like, you know, like kind of up and to the left, right? It's not over there; it's on the right side of it, right? Okay, so we can be sure of Fg there. So then let's just kind of do Fg sine theta. No, sorry. That is going to be our Fgy, which is going to come from Fg cos theta, right? So that's mg cos theta, and that is our Fn value, right? Sorry, this is an Fn, this is F. Okay, and that's going to be equal to our Fn value. Okay. If you're not comfortable with that, we can kind of do some review with some free body diagram stuff, but what that means is our force from A to B is just mg cos theta. The distance is, well, do we know? We don't know how high, right? No, we don't really know, but we did represent it as h in this equation, how high it was, right? And so we should be able to sort of like use that angle with that h value to find the hypotenuse length, right? So it should be, what should it be? That the sine of theta is h over r, you know, let's call this, do we have an x value? I don't think so yet. Right, so let's call that our x distance, the length of the ramp there. So that means our distance is sine theta. So this is mgh over tan theta. Okay, plus work throughout this journey here, the circular journey here, well, that's half of the circumference. The circumference, and they tell us that it's fk, right? So we're allowed to represent it as fk. The distance that we travel, the sort of delta d there, is half of the circumference. So the full circumference would be 2 pi r, so it's half of that, so it's just pi r. And we don't really have any representation of anything, so we would just kind of do some rearranging and figure out from what height, so we're going to have to rearrange for h here. All right. So, okay, so let's do that. So mgh minus 2 mgr is equal to 1/2 mgr plus mgh over tan theta plus fk IR. And now rearrange for h, right? So bring everything over there. So do tan theta. Okay, so h is equal to, we're going to add, so that's going to be 2, so it's going to be 5 over 2 mg r plus fk pi r all over, oh gosh,
He's sharing our culture with people
all over
all over the world. And honestly,
mg
I still can't believe it.
minus mg over tan theta. Okay. And I think we're okay with all that, right? Because we had, those are all of our generals. So that's our h value. Right. If you're not comfortable with that kind of rearrangement, we can do it a couple steps, but you know, maybe it's a challenge for you. I think that's right. So let me just double check. So 2.5, yeah, 5 over 2, and then I just have this. This one's going to go over there. It's going to be h, yes, and then because we moved over there, was a minus, and we're going to divide it out because we're going to factor out the h, and it's going to be mg. Yeah. I'm confident. Okay. So, there it is. Okay. Take a little break, and we'll be back shortly. All right. Enjoy. Be should we can leave it on this maybe? There we go. All right, we'll be right back.
as well. It's just as well.
There we go.
St. Paul, what's happening? Night 2? Thanks for coming out. This band's called Death Cab for Cutie. We're from Seattle, Washington.
Listen to Chill Hop with your screen locked and study uninterrupted. Try YouTube Premium on us.
If only you'd have known me before the accident. For with that grand collision came a grave consequence. Receptors overloaded, they burst and disconnect. Till there was little feeling. Please work with what is left. Oh, I may not be flattered, but you've never been here before. So there's no need to mention that you've no first anymore. But if you let me be your skyline, I'll let you be the wing that reduces me to rubber that looks safe from far away. I don't know why, I don't know why I return to the scenes of these crimes where the hedgerows slowly wind through the ghost of Beverly Drive. I don't know why, I don't know why. I don't know what I expect to find. Where all the news is secondhand and everything just goes on as planned. You wanna teach but not be taught. I wanna sell but not be bought. So let us not be lonesome. So let us not be lonesome. Lost in between our needs and wants. I don't know why, I don't know why.
your personal guide to the world of K-pop. Sign up for YouTube Music Premium with 1 free month.
His head was a city of paper buildings and the echoes that remain.
Alright. We back? Should we just change it to back? Be back. Alright. Okay. I think actually we have to grab our next chunk. Let's see if we can do that. So, should we? What do you think? What do you think? What do you think?
Snowing softly as she hunted for her keys. She said she never envisioned.
Alright, I'm gonna actually think this is still just a little bit too low. Go down here. Boom. That should be okay. Cool. None of those are any good. Okay, sorry. Should be ready with this, but you all some questions. Huh? Alright. I don't want to do functions right now. What should we do? Some biochem? Brains. Patient. Choice. I don't do choice. Come on. Dun, 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 dun.
Glove compartment isn't accurately named. Everybody knows it. I'm proposing swift orderly change. Behind its door, there's nothing to keep my fingers warm. All I find are souvenirs from better times.
Okay.
For the queen
I'm gonna have to put a big message up.
light's fading needs to find yourself a better life.
All right.
I was searching for some legal documents.
All right.
As the rain beat down on the
Those are no good.
when
Keep
I
looking.
stumbled
We're looking.
upon pictures I tried to forget. And that's how this idea was drilled into my head. It's too
I
important
want to keep doing
to stay the way it's
physics.
been. There's no blame for how our love did slowly fade. Now it's gone. It's like it wasn't there at all. Here I rest for disappointment and regret. Could I, lying awake at night, there's no blame for how our love did slowly fade. Now it's gone. It's like it wasn't there at all. Here I rest.
All right. I love these. Let's do them. All right. Let's do it. So, I think these are two different ones. Yeah, these are two different ones. So, let's do the first one. We have. Are these supposed to be equal signs?
Thank you very much. How's everybody doing? Okay? All right.
Yes, they are.
Pace yourself. It's going to be a long night. We're going to play something old, something new. And we're playing some new stuff because we have a new record out called Thank You for Today. It came out 6 weeks ago.
Boom.
So
Okay.
we're going to play some tunes from it.
So
including
V
this one.
total. Oh no! Don't tell me. Okay.
Digging for gold in my neighborhood.
Okay.
Where all the old buildings stood. They keep digging it down and
Okay.
down.
Loading up. Here it is. All right.
The swinging of a wrecking ball.
There it is. Alright, let's get it. We're ready. And maybe we can change the music actually, since I don't really want to listen to it. No thanks. No thanks. No thanks. I want to listen to an album of some sort. Album. Listen to the old Adele. Old album. It's my girl right here. See, I don't have her. So.
was all you, none of it me. You put your hands on my body and told me.
Oh yeah, it's kind of
Tell me
full
you were
class.
ready
Okay.
for the big one, for the big jump.
So these are the same, so these are both 60 ohms. Sure. Okay, that's gonna make things nice. R3 is 250 ohms. R4 is 325 ohms. 5 is 260 ohms. The total is okay. So I mean, we have VT. We're asked about IT. So all we need is RT. Right? So to get to RT, we don't know RT yet. But to get to RT, we're gonna have to combine all these circuits. Right? So what we sort of fundamentally have is 3 things in series, right? So there are 3 things in series, and those 3 things are kind of like R1 and 2 combined. The second one is just R3 on its own, and the third one is R4 and 5 combined, right? Do you agree with me? You better. So we now just have to sort of solve for each of those on their own. And I'm actually just going to put an arrow because I'm not going to sort of look at the equation, because what happens with these parallel circuits is it's 1 over the total is equal to 1 over RB plus 1 over RA. Either one, right? That could be A and B. Right? So let's kind of like put that into an equation here, right? And it is not true. It is not equal. So like you might ask the question, is if I flip all of them, is it true? You know, that I could flip all of these? No, then why would we ever, if the equation was just this, why would we ever give it to you like this then? Right? They are not equal to each other. This is not true. Absolutely not true. Okay? Oh god, this file's getting too big. Okay? Absolutely not true. Okay. So let's get that out of here. So what do we have? Come on, give it to me. Alright, just give me 1 second.
They say that time's supposed to heal you, but I ain't done but
Hello.
Can you hear me? I'm in California dreaming about who we used to be when we were younger.
Come on now.
And free.
Come on now.
I've forgotten how it felt before the world fell at our feet.
Oh.
There's such a
Let's not do any erasing.
Between
Okay. No, actually change this.
Hello from the other side. I must have called 1,000 times to tell you I'm sorry for everything that I've done. But
Okay.
when I call you,
Go on here. Okay.
seem to be home.
Okay. It's okay. Oh god. Oh god. Don't do that. No, no, no. Oh, gosh. Okay.
Hello, how are you? It's so typical of me to talk about myself and sorry.
All right.
I hope
Sorry about that.
that you
So
will. Did you ever
this
make
1-2
it
combined
out
is going to
of
come
town
from
with the net?
this
It's no
equation.
secret
This is going to be the same.
that the both of us are
So
running
this is not
out
45. This
of
is 4,
time.
5, right? Coming from 4 and 5. Okay, so let's sort of do some rearranging here. So we get 1 over R1 is 60, and R2 is 60. So this is really just going to be 2 times that. So this is 2 over 60, which is 1 over 30. And that is the 1 over R12. So R12 is equal to 30, right? Not 30 volts, 30 ohms. It's a resistance. Okay, so R12, that's 30 volts. So 30 volts, 30 ohms. Okay? R3, we already know. R3 is 250. And R45, let's kind of solve the same way here, right? So let's just... that equation comes there. Alright. So, let's just go over a little bit. Down just a tad. Okay, now, so, R4 and R5, now those are a little messier, right? So that's 1 over R4, let's just be proper about this. And then plus 1 over 260. So this I would just use a decimal for, right? So 1 over, or you know, maybe I'll ask my calculator to do it in fractions, keep things in fractions. Is that a good idea? Maybe, yeah. So let's do that. So let's, if we can remember how to do this, so plus, you know, we can obviously also do common denominators and do this our own, right? Okay. So it's about 144. Repeating is our R1. Sorry, R45. Okay, so let's just kind of round it here. We'll say 144 ohms. Right. And so there it is. And that's our R total. So let's add these all up. We get 424 because those are 3 in series. That's how we add things in series. So that's 424. And so now we can just E equals IR. So 35 equals I times 424. So I equals 8, 3. I think we were just given 2 sig figs mostly. And that's IT, so yeah. So we could also say 83 milliamps. That's our answer there. Right. So bad. Let me just do some rearranging here. And our answer is 83 milliamps. All right. Beautiful. Is that all we were asked for? Yeah, IT. Right. So let's call that IT. Beautiful. All right. What else? What else can we do for you? What else could we possibly? Oh, let's do the next question. Right. This is an interesting question. This is something that, as a homeowner, is a perfect example of why I will need some skill in physics moving forward. So, particular circuit contains 3 lamps. Okay, I'm gonna have to go ahead and switch this up. I hope that's okay. Came true. Alright. It's time. So, particular circuit contains 3 lamps. Lamp A turns off when lamp B is turned off. Okay. So lamp B somehow controls the flow to A. Sure. But stays on when only C is turned off. Lamp C stays on when either A or B is turned off. Draw a circuit diagram to show arrangement of the lamps. So, because we can kind of go higher and higher in the hierarchy of dependency, so who depends on who, and who depends on, and that person depends on this, and this person depends on this, or bulb depends on that. Let's kind of go higher and higher, and we'll start with the one that sort of like has, you know, seems to be doing its own thing, and everything depends on that one. So, lamp A turns off when lamp B is turned off. So lamp B is kind of the one that's, you know, being dependent on it, okay? This stays on when only C is turned off. Okay, interesting. Lamp C stays on when either A or B is turned off. Okay, so both of those are depending, so C is depending on A and B, but again, B kind of wins that hierarchy. So it seems like we only really have to worry about that kind of like, but stays on when lamp C is turned off. Right? So I'm going to draw lamp B first. Okay, for my circuit. For now, let's just put it in series, okay? Like, you know, this wouldn't be the case if they were all just in series, right? This wouldn't be the case, that lamp A would turn off when B is turned off. Well, that would be true, yeah. but it wouldn't stay on when C's turned off. If C was turned off, that would break the that would break the circuit, right? So okay, so then let's imagine instead of C, us needing to kind of depend on C, let's just try putting some things parallel. So what would be the case here? So lamp A turns off when B is off. Yes, that's still the case, right? If B is off, that's a cut in the circuit before we even get to A, right? But it stays on when only lamp C is turned off. Okay, that would still be the case. Lamp C could be turned off and A would still stay on, right? Okay. Lamp C stays on when either lamp A or lamp B is turned off. Ah, no, because if right now if lamp B, like that's true if A is turned off, then we just have a series between B and C, right? But if B is turned off, that's cutting the switch to C, so C shouldn't stay on. So I think C needs to kind of go, you know, still be parallel, but be parallel a little bit earlier. And now let's see what happens. So 3 lamps. When lamp A turns off when lamp B is turned off. Yes, that's the case, right? B is kind of controlling the flow to A. But stays on when only lamp C is turned off. Yes, if lamp C was turned off, then we would just have the circuit BA, right? Okay. Lamp C stays on when either A or B is turned off. Yes, that would be the case. Like, if whatever you were doing with A or B, we would still be able to complete the circuit by going through the C loop, right? I think we've done it. I think we did it. I think we did it. Beautiful. Let's cement it. Let's lock it in, Regis. Boom. Okay. Not bad, right? And this is how you can kind of, you know, this is how like light switches kind of can be controlled so that regardless of this one being on or off, this still stays on, or this one kind of controls the flow to that one, right? So like no matter what you do with A or B, or with A, it kind of depends on B being on, right? So B could kind of be like a master to whatever's happening in A, right? Okay. So wait, can you see my cursor? Just want to make sure you can. Yeah. Shit, that is. Yeah, you can. Okay. Cool. So let's keep it going. Let's keep it going. Alright, pulling up some more questions here. Okay.
It's been so
like this one. Alright. Do it. Right? Oh. What do you got? Okay, sorry. Just getting the next little question ready. We'll shift to chemistry. Okay, so let's do it. Sorry. So 38-gram bullet is fired with a speed. Okay, let's get a drawing going. Drawing right away. Right? Boom. One. Drawing. Whenever we can. Right? So let's do it. We got our drawing here. Little drawn box. So we've got a bullet that's fired. The speed of 180 meters per second. Okay. Into a pendulum sandbag. That is free to swing. Okay, so it's free to swing. So it's kind of like gonna go this way. Okay. And this thing is gonna, you know, let's exaggerate it a little bit, but it's gonna be kind of like impacted, and it's gonna hit it, and it's gonna kind of like come up a little bit, right? Okay. So the question is, how much will it be bumped? Right? Okay. So we've got our drawing, right? Alright. Let's do this. It's a little smaller. Okay. So yeah, the question is this delta H. Right. So, because that's the height difference between those two. Okay, so next is our inventory. Okay, so this is one. So let's do another one. Let's make this our inventory. Sorry, color coordination is off the chain in this problem. Boom, we don't know that, we're looking for that, right? So we kind of, let's say the V of the bullet, right? And remember, we're going to kind of have a like moment of impact. That's one time that I'm going to be interested in. And then another time I'm going to be interested in is, you know, after all of the energy of the bullet has been transferred to the beanbag, you know, let's consider the bullet joining the beanbag, right? Then what height does it get to, right? So, okay, so let's keep kind of chugging along. So the velocity of the bullet, let's sort of say at 1 is, we don't really know the mass of the bullet, and we don't really know the mass of the, like, sandbags. Let's call that MS, right? So let's just kind of, like, have those there, but we don't know them. So, VB1 is 180 meters per second. What is VS1? What is the velocity of the sandbag at time 1? Well, it's just sitting still. It's just sitting there before it gets shot with this thing, right? And then it has some movement, but it ultimately uses all that velocity to get to a time 2, right? So let's maybe kind of yeah, I hope there's no kind of confusion between these, right? So, you know, maybe we can actually even just use A and B here. Be better. Okay, so let's do this. Okay. So, boom, and then up, boom. And then we'll do that, and boom, and then we'll do that. So, we don't all know that. Anything else, really, that we're going to need to know, right? Because keep in mind, we're going to kind of like be talking energy at 1 is equal to the energy at 2. Okay. So, okay. So, what are all of the energies, right? So this is now kind of like time for our, you know, I'm going to kind of sort of include this. Maybe I won't, actually. Just do this. And we'll be ready to add to that if we need to. Okay. But we also have some masses. Oh, we have some masses, right? Why did I say we didn't have masses? I don't know. What I'm thinking. Don't know what I'm thinking. Okay, so the mass of the bullet is 0.038 kilograms. Why did I do that? Because it's grams, right? Don't be caught. And then 5 kilograms is our sandbag. Okay, cool. So let's kind of like tackle C here. Now let's just do this. Let's make this a tiny bit smaller here. Boom, 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 boom. Okay, so let's tackle C here. We're gonna kind of like equate, remember, the total energy. Whoa! Boom, boom. Okay. So we're going to, yeah, we're going to have the sort of total energy here of including the bullet, right? Remember, the bullet's included in that, and the energy at 2, which is the bullet and the block sometime later, right? It's both of them. So don't be kind of caught by the fact that it's, you know, only one of them. It's only the sandbag. The bullet is there too, right? Okay, so at 1, we're going to have an EK of the bullet. We have an EK of the sandbag, right? Well, actually we don't, because at 2 we don't either, right? So the reason we include this is because that's changing, right? That's going from 180 to 0. So that's going to change, right? Okay, so only the energies that are going to change. Well, our EG is going to change, right? That's of the bullet and of the sand block. So let's call that BS, okay? So this is BS. Nice to meet you. Okay, so is that it? Is that all we need? I think that's it. We don't lose any other energy, right? So what about E2? So there's EK of the bullet again. And this time it's got to its max height, so the bullet's velocity is 0. We're only going to use the bullet's mass for that, right? Because it's only the bullet that mattered. Just like that with velocity, only the bullet that mattered, right? And then we're going to do the EG of the bullet and the sand block, okay? And that's for like some 2 spot, right? That's 1, so that's 2, okay? Okay, so let's do it. So EK of the block in the 1 circumstance is 1/2 m of the block V in the 1 circumstance. So that's mass of the block is 0.038. The velocity of the block was 180 meters per second. We square that, it's pretty fast, but because it's a low mass, it's not that much energy. I mean, it's quite a bit of energy, right? But so it's 2. We can just kind of keep everything in joules for now. So I'm just going to kind of keep a bunch of decimal places for now, or a bunch of sig figs. 2462. Okay. So that's EKB1, right? And EGB1 equals. So EG, that means gravitational potential energy. So that's mg delta H, or really just mgh, because remember, we get to choose where our h equals 0 spot is. So where is our h equals 0 spot? Almost always it's a good idea to use the ground, and if not the ground, then the lowest spot that anything goes. So let's call that our h equals 0 meters spot, okay? So what that means is at 1, this is just 0, right? Because it's at a height of 0. So mgh is just 0, right? So that value is 0, right? H equals 0. And here, it's at its max height, which means the bullet is no longer moving, right? So this energy here value has to equal our EGBS2, which is going to be our mg delta H, because it's EG, and BS, that means the mass is the mass of the bullet and the sandbag, right? So maybe we kind of add that to our inventory here and just say, hey, if you're going to need it, the mass and the sandbag added together is 5.038 kg, right? Not so crazy. Okay, and then G, whoop, we changed to blue. Okay, so, and then G, and then H is delta H. How far did you go? Well, that's actually what we're trying to find, right? So we now have something that we can equate these to. We can say 2462, which is this, is equal to, well, this is 9.81 times 5.038. This is 49.4 2 times delta H. So we can solve for delta H. And weirdly enough, sorry, I got a little spooked out here. But it does make sense. This is close to 50, this is close to 2500, so 50 times 50 is about, yeah, and that's meters. Is that meters? Would it be meters? $50 meters in the air? That seems a little bit suspect. What? That's not good. Okay, so that does that. The problem with that is it's crazy. 50 meters in the air. So something went wrong. Okay, I found a mistake. I just added this into my calculator wrong, right? Hard to kind of catch because it's such a weird number here, but should have probably caught it. But let's just say this is our new value. So let's check to see if that makes a little more sense. Seems a little bit more reasonable. It's still kind of high. So let's just double check that we haven't done anything crazy here. So, because it might be worth asking kind of like what's the, momentum of that collision look like, right? So that is sort of like a M1 V1 plus M2 V2 is equal to M1 V1, sorry, because they kind of join up, it looks like this, right? Call this V prime, the new velocity that they're both traveling, right? So let's maybe do kind of some math with this. Let's say that the velocity of the block was 0, and this one was 180, so this is 0.038 times 180 divided by 5.038. That is our new V prime. And now we can kind of use pretend like we just have the kinetic energy from that V prime of the two of them sort of traveling at that new speed, right? So this calculation might look a little different, so let's try it that way. And we might have even screwed up the other one, but let's just see if we can try it this way. So now we have 1/2 MSB, this is SB, right, or BS, that's what we called it, MBS, and then V prime squared, right? So, sorry, the V prime here ended up being 1.36, which seems a little bit more reasonable. And so we square that, and we multiply that by half, and then also by 5.038, and we get, this seems a little bit more reasonable, 4.64 joules, right? So our problem was we weren't using momentum to analyze this first collision here, right? And we were sort of assuming that kinetic energy is conserved. It's not necessarily true. Momentum is conserved, not necessarily kinetic energy. So, okay, so then let's see if this kind of makes sense here. So 4.64, and then divided by 49.42. This seems like it should be a little bit better. So this is, this is a little bit better, a little more reasonable. So let's do this. So 9.4 centimeters. Okay. Okay. Alright. So, okay, let's take a little gear shift here. Just wrap things up here. It's a little bit of a challenging. Let's actually do. Let's do this. So, all we're asked to do here is balance. Okay. Balance these equations. So I'm gonna first kind of put our two equations, put them on a board, and then you can take a look at them. Just gonna grab a little refill for my water. Okay, and then we can tackle both of these. Okay. So let's do this. Let's do this. Let's say be right back. Try this one. Okay.
I've been down to Georgia. I've seen the streets in the west. I've driven down the 90. Well, hell, I've seen America's best. I've been through the Rockies. Well, I've seen Saskatoon. I've driven down the Highway 1, just hoping that I'd see you soon. 'Cause I'm coming home. 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 Coming home. Well, I've never been to Alaska, but I can tell you this. I've been to Lincoln, Nebraska, and hell, you know it ain't worth shit. I've been through Nova Scotia, Sydney to Halifax, but I'll never take any pictures, 'cause I know I'll just be right back. 'Cause I'm coming home. 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 Coming home. Well, I've seen a palace in London. I've seen a castle in Wales, but I'd rather wake up beside you and breathe that old familiar smell. Well, I never thought you could leave me. I figured I was the one, but I understand your sadness, so I guess I should just hold my tongue. But I'm coming home. I'm coming home. I'm coming home. I'm coming home. Coming home. I'm coming home. chances. You told me life was a risk. I just have one last question. Or will it be my heart?
All right,
Or will it be his?
let's do we. Boom.
Coming home.
Okay,
I'm coming home.
so
I'm coming home.
gotta balance these two equations.
I'm coming
So
home. I'm coming home.
what do we know?
I'm coming home.
Is it a good idea? What? What in the?
Coming home.
What in the?
I'm coming home.
Cute.
I'm coming
Anything crazy, please? Cute. Okay. So, sorry. So, should I be taking? Should I like? What should I start with? Should I start with oxygen? Oxygen is in every one, but in fact, I'm never really gonna look at the oxygens on their own ever at all, okay? Because the oxygens are always found with another partner. So what I'm gonna look at is the groups. I see some CO3s. I see some PO4s. Those I'm gonna do as if they are just one thing, just one atom. The other things I have are Ca and H. So let's just kind of like start with a count here. So we have one Ca, we have one CO3, we have 3 H's, and we have one, I don't know why I did my ones differently, but whatever, one PO4. Okay, so then H's right now are kind of like on our mind. Let's do the count over here. Count over here is a little different. So the count over here, how many CO3s? We still have one, so that's okay. But we have 2 PO4s. Okay, so that already tells me that I'm gonna need to kind of like start, and this might be a place where I would start is by putting a 2 here, right? So that already brings this up to 6 and this up to 2, right? So maybe we don't do it that way. Maybe we do this. Maybe we say, let's not make that huge anymore. I think it was this one. Okay. So let's say that that's now a 2 and that's now a 6 because we doubled them, right? So now those match up. Okay, now what about Ca3s? So, sorry, Cas. So we have 3 of them, right? So that tells me that I'm going to need a 3 over here to put in front of the 3 Ca3s. So what did that do to the Cas? It gave me 3 of them. That's good, but it also changed the CO3, right? Which was with it. For every Ca, there was a CO3. So now there's 3 CO3s. So now this is not balanced, right? And this was not going to be balanced anyway because of the hydrogens. So let's kind of hope that those two now match up based on this change here. So this is going to need to be a 3. So that we have a total of 3, so that those totals are okay. And now how many total hydrogens do we have? We have 6 hydrogens, which is what we wanted, right? So that's how we go about that balancing. Okay, let's do the next one. So it's kind of, I mean, part of it is about, oh wait, I'm not going to have a lot of those anymore, so let's not do that. So what things do I have here? I have PO4. I have NH4. I have PB. I have NO3. Right? And those kind of just like change partners. Right? Okay. So this one's going to get nasty, I'll tell you that. And I can tell that because of the 3s and the 4s, right? The 4s and the 4s and stuff. But let's just see. So for now we have 1, we have 3, we have 1, and we have 4. Okay? So already I'm kind of looking to this one and saying, okay, that one has to be a 4, right? That one at least has to be a 4 to match up with the bottom, right? Let's just start from the bottom this time. So what that means is we have 4 of these. Okay, now that means we're going to have to do some matching up, because that's the only source of ammonium, right? So what that means is we're going to have to do times 3 over here and times 4 over here, right? The first number that those are going to line up at is 12, right? So that means this becomes 12. So this becomes 12, which changes this. That becomes 12, right? And this becomes 12 because I multiplied this by a 4. Right? Okay, so then this 12 here now doesn't match up with this, so let's make that match up. There were 4 of those, so I'm going to need 12 by getting 3. And so there's now 3 PVs. And how many PVs do I have over here? I have 3, that's nice. And how many PO4s do I have? I have 4 PO4s. Uh-oh. So we're going to have to do some PO4 rearrangement, or did we forget that a 4 here is going to change this to be a 4 as well, right? So we're actually okay there. So that's it. We're done. Okay. So the process is kind of like following, going down and saying, oh, okay, this doesn't match up, so I gotta make those match up, and now that changed that, so I gotta make these match up, now that changed that, now I gotta make these match up, and now, oh, okay, now that's perfect, right? That's kind of what this process looks like. It does sometimes look a little nonsensical, but we're kind of following a thread almost always, and usually we start with the simple threads. So like, I could see just by looking at this, my CAs don't match up, I'm going to need to start with that 3. Okay, so now what are the consequences? CO3. So then I'm going to need a 3 there. Okay, now what are the consequences there? That means hydrogen, so that means I'm going to need a 2 there, and look, I already have all 3 numbers. I'm done. Right? So that's kind of like the process for balancing. Okay? So I think that's a good place to leave it. Why don't we leave it there? We've got a nice little kind of PDF from today. So this will be available somewhere. I'll make sure of it. But yeah, it's been a pleasure. And if you're checking this out in the future, then yeah,